Good morning, everyone. Welcome to the JKMRC Friday Morning Seminar Series. On behalf of the University of Queensland and the Sustainable Minerals Institute, I would like to acknowledge the traditional owners and custodians of the lands on which we meet today. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connections with country, and we recognize their valuable contributions to Australian and global society. So for this seminar today, it's my pleasure to welcome Dean David. Dean has 43 years of experience in mineral processing, covering flowsheet development, operations, management, and consulting. Holding a bachelor's in metallurgy from SAIT in Adelaide in 1981, Dean began his career with CRA, later Rio Tinto in Broken Hill, and later working for Wimmera Industrial Minerals and Argyle Diamonds, gaining extensive experience in several aspects of mineral processing technology. With 7 years at JK Tech, including a managerial role and subsequent positions at GRD Minproc in Perth, Dean has developed skills in comminution, geometallurgy, scrubbing, iron ore concentrate circuits, mine-to-mill optimization, dense media separation, flotation, plant modeling, ore characterization, and many other processes. He remains an integral part of the Minproc team, now under the umbrella of the global engineering company Wood. Today, Dean will be presenting his seminar titled Know the Minerals, Know the Job. Pretty cool. And so please, let's give a warm welcome to Dean.
That's all working correctly? Yes. It's great to be here. I was, as you heard, I was in this place for 7 years or so, and managed JK Tech Consulting for about 3 to 4 of those years. And I consider my time here as actually a PhD by stealth, just getting to see the entire mineral processing world from this environment here, which is a great conduit into that. Into the global mineral processing side of things, which has, I think, exploded quite a bit since that time. I now look at things like LinkedIn and I see massive things starting up and going in all sorts of places and thinking, this is good. And it's all built on past knowledge and understanding, and a lot of it developed within these walls. I want to talk today about minerals. Minerals are basically what we deal with, and I'll go through a few things. The first slide, however, shows something that caused me grief during my studies, and we have at the top a nice specimen, but it's a black specimen. Something similar to that I called tourmaline in my studies in Adelaide. And I lost a mark because it was actually a black quartz. And I realized at that point that minerals aren't necessarily what they first appear to be. And you can see down the bottom some nice white quartz and some nice tourmaline crystals, nice and black. And behind that, you can see what is the lifeblood of mineral processing these days, which is the images of particles that we get from QuempScan and MLA, which is now a combined effort. And both of those technologies I had the privilege of being involved with right at the commencement of both of them. Just to, what's going on? I think it's turned itself off. Okay, that's better. That's better. Just to for those who aren't familiar, that might be listening online or in the room even, we have 3 things that we deal with: rocks, minerals, and elements. Elements are usually things we chase, like copper, whereas the minerals and rocks are the things we have to deal with, that Mother Nature has delivered to us. So just a few quick definitions. Basically, a rock is made from minerals, and there's 3 sort of classes of igneous, metamorphic, sedimentary, and examples are granite, basalt, sandstone, and there's about 5,000 others, including things like kimberlite and lamperite and anything you want to think of that is a mixture of minerals sitting out there in nature. And most of what we see around us is rocks. At the other end of the scale, there's the elements. Of course, there's about 92 of those that occur naturally, although some people think there might be some elements out there in the 150 realm instead of 90 for 92 for uranium, sitting in stars or something out there that have been created in the universe. So who knows what is actually in the broadest definition of nature. But on Earth, we obviously only have up to uranium, and then we've made a few more, but none of them hang around for very long when we make them. And things like iron, silicon, oxygen. Of course, these are all the elements that make up what we can see, make up the rocks and the minerals. So where does the mineral sit? Again, it's found in nature. There are, as of the last few days, 6,031 recognised by the IMA, and they are typically defined by their chemical composition. However, there are also things like a composition template, where they put, instead of the number of atoms, they put an X and an X minus one or something in there to say, here's the template. Or there might be a spectrum of compositions for a mineral. So that's 6,000 or so really is an infinite number because almost every mineral has its own composition. There's only a few that every time you look at them, they're actually the same in nature. A lot of them are quite different when you delve into the details of what you're really looking at. And I wanted to go through my career, which is as happens when you wait a while, has spanned quite a number of decades, and just I've got about 7 examples of different mineral experiences that I want to share with you, and just show you some of the things that I've had to deal with, and sometimes it looks very simple today to say, oh, we should have sorted that out earlier. But the tools we have today are so much better than what we had in the 70s. They started to get better in the 80s, then they got even better again. So as a vacation student, I went to Broken Hill and got stuck into a project there that they threw at me, which was trying to reduce the arsenic levels in the flotation concentrate, the lead concentrate. And for those of you that don't know, Broken Hill probably produced the best lead concentrate in the world. If it dropped below 70%, there was something really, really wrong. Normally 72 or 70, 71% lead in the cons, getting close to pure galena. And arsenopyrite, which is iron arsenic sulfide, was the main culprit. And then I started to do some work on that. I went underground, found some nice shiny stuff that the geologists told me was some nice arsenopyrite. So I had some pure mineral to work with, as well as the various the feed arrangements for the plant. And then I started doing test work and madly floating, and I then took that project into my final year at SAIT, which is now part of University of South Australia. Anyway, at the end of the project, I then thought I'd better check on the composition of this mineral, and the arsenopyrite on the left is a bit tarnished. Normally it's very silvery. The one on the right is lollangite, which is FeAs2, and I had lollangite. I've been working the whole program on a different mineral than I originally thought I was dealing with. Fortunately, it floated and behaved in a very similar fashion to arsenopyrite, and it was still relevant, but it just it taints the the results that you're trying to claim if the mineral you've been dealing with and characterizing isn't quite the one you thought it was. And basically, you can see there, arsenopyrite has an SG of 6 and lowangite's almost 8. And this is one of the things that knowing the mineral that you are dealing with gives you. And these are a few more things. It gives you the composition, of course. And unless you delve in more deeply, it's only a theoretical one. It gives you a possible concentrate grade if you can get that mineral by itself into a product. The SG gives you the hardness, typically the geological reference of a Mohs hardness scale. What does it scratch and what doesn't scratch it or whatever. It gives you the crystal form it's likely to be in. It gives you other methods for identifying it. It tells you about how it's going to respond in flotation, whether it can be leached by acids of various types or alkalis, whether it gives you the ability to reference other projects that have recovered this material previously, and so you can start doing some research on what people are doing now. You can then start to look into marketing and what sort of specifications concentrates need to be and what other minerals or elements are a problem in the final concentrate of this particular thing. You can look at things like global abundance. How rare is this thing that you found? And there are other things that you can add on to that as well. So actually putting a name to the mineral that's in front of you is quite a empowering thing in the business we're in. Moving on to the second example, I was working for Wimmera Industrial Minerals, which was part of CRA, looking at mineral sands in Western Victoria near Horsham. And we had zircon, and we had ilmenite, and we had rutile. Then we had this stuff in the middle called leucoxene. And leucoxene is formed when ilmenite degrades. So ilmenite degrades, you lose iron, it goes to TiO2, and you get varying proportions of TiO2 and Fe based TiO2 with ilmenite. So leucoxene is a spectrum mineral, and it has its composition is not really defined. We had a problem in that we couldn't get silica out of this particular species that we were dealing with. And across the corridor from me, because I was working at Clayton in Victoria in CSIRO labs at the time for CRA, and across the corridor there were some people playing with computers and electron microscopes, developing this thing called QuemSem, as it was at the time. So I wandered across the corridor and said, can you look at this particular species? Or can you find the silica? That's the question. And be aware that the question is the most important thing in actually needing to understand what the mineral is about. Because if you don't have a question about a mineral or a question about a problem, why are you trying to find out more information? You have to have the question. I often see people say, I've done the mineralogy, I've done QuemSem, QuemScan on this stuff. And you look at it, and basically somebody with a skilled mineralogist looking down a microscope could have given you those answers. You have to have a question like, why can't I get a good concentrate after grinding to 53 micron P80? And then you say, right, I need to get a sample that's been ground to 53 microns, has all the problems in it, and then we examine that. So define your question, and you're halfway there. So, and these particles here, you can see some white on some of those black particles. That white is pure TiO2, and the black is the ilmenite. And when you, actually it's more like a yellow here than a white. When you put this particular material into the newly developed QuemSem system, unfortunately I don't have the original pictures, but we were searching for leucoxenes, which were mixtures of ilmenite and and rutile, or TiO2. And what we found in amongst it was large numbers of particles like the one on the right, which were basically layers of a few microns width, alternating between TiO2 and SiO2. And you can't recover that TiO2 if you don't want your silica. You cannot liberate that material. It very quickly became clear that a significant proportion of the TiO2 we were chasing was never going to be sensible to be put into a final concentrate. So that was a big eye opener for both us and for the guys at JKMRC, because they had typically looked at Broken Hill or mineral sands concentrates from the East Coast and West Coast, which were nice, whereas this stuff was quite different. And back then, to get an image, what you had to do was you had to get this big light shield with a camera at the back of it and put it over the computer screen, and then push the button and take slides. So that was, this technology had developed faster than the ability to actually deal with it. And when you got information from it, it was in the form of a stack of printed A3 fold paper with holes in the side that would be up to that thick. And then you'd have to work your way through that to find the information you're after. Of course, having got this answer, suddenly a whole world opens up for me of, what are we dealing with here? And what else can this technology give me? So I had a whole lot of questions, and I went to them and they said, yes, we can deal with those questions. And to me, that was just opening up a world of mineralogy that wasn't there before at all. And the joy of that time was working with some of the pioneers. Paul Gottlieb, Richard Jackson, and David Sutherland were involved in the work, mostly the first two in the actual work that I was involved with. And you can see that's an award being given to Paul Gottlieb in the middle, who for the development of JKMRC by CSIRO. And you can see down below there a bit of an outline of what was needed at the time to take the information that was being gathered and turn it into something that was useful to then be interrogated by a process engineer. After 14 years at CRA, I was still at CRA. I went to Argyle Diamonds. Now, Argyle, obviously, diamonds, quite interesting in a mineralogical sense. But Argyle broke the rules in the diamond world as well. And diamond deposits in places like South Africa were discovered by searching for indicator minerals, various interesting minerals that typically occur in kimberlites. But they actually searched for diamonds and found them in the case of Argyle, which was almost unheard of in the whole business of the minerals and a business of diamond exploration. And it turned out not to be in kimberlite anyway. It was in a thing called laterite, which is a much harder and stable rock. And if you look at a typical day at Argyle, you'd start off with 25,000 tonnes of rock. You'd then put it through a dense medium separation, and you'd finish up with 25 tonnes of heavy minerals by dense medium. You'd then put it through X-ray sorting, and you would get 50 kilograms of about 50% diamond. And then they change from hydrofluoric acid to molten 500 degree sodium hydroxide during my time there, and then you finish up with a clean product, which is essentially 100% diamond at the end of it. And 25 kilos. So we used to say we would get a bucket of diamonds every day out of Argyle from 25,000 tonnes of rock. But here we have the three unique properties to diamond that are being used in this flow sheet, which is its SG in the dense medium, its ability to fluoresce when you hit it with X-rays, and its ability to survive molten sodium hydroxide. But don't get the temperature above 600 degrees, because then you start to lose your diamond. It actually dissolves in the molten sodium hydroxide. I had about 6.5 years there, and that was a fantastic time. Mostly I didn't see diamonds. So I was just dealing in that world of mineralogy in action, if you like. At JK Tech, came here, and one of the early things I was asked to do was to go down to Savage River. And during that time, after a year or two of going down there for various reasons, they then said, oh, we've got a TiO2 problem at Savage River. So we've got a contamination of our magnetite concentrate that we've made. Can you get that TiO2 out? I got examples of that material, and I haven't got photos, unfortunately. But when you looked at it, the magnetite grains all had these lamella at nice angles to each other within the grains of TiO2, which were basically impossible to remove. And these are, we're talking 10 micron or less in terms of width. And in a situation like Savage River and most magnetite operations, the final grind size you go to is set by what you're doing downstream. And you need to attain a blane, which is a measure of surface area per unit mass. And that means you're stuck with a P80 somewhere around about 40 microns. And you're never going to do anything to try to get 5 microns out of the system. You can reduce the TiO2 a little bit, but you'll never, if you've got it in there in a percentage, say 1%, you'll never take it to 0.5%. You might get it down to 0.9 or 0.8 with the right processing. Again, the client sort of hoping to have some sort of magic in terms of getting a better product was unable to do it. And that's the message you need to get as quickly as possible. If it's not possible, find out why, deal with it. And at Savage River, there was 2 ways to do it. You avoid the ore that's got the high titanium, or you do blending. And for other reasons, they did blending. Something else I was always harping on about for about 7 years, and eventually they introduced it. And that was able to smooth out the TiO2 levels in their products as a side benefit. And that's a picture of the in-pit crusher and the blending stockpiles at the top, and the bottom one is their dedicated pelletizing plant up at Port Ladder on the north coast of Tasmania. And while here, I also worked with another pioneer, which was late Dr. Yingu, and we sat down in his office, which was on the ground in the car park, basically, many times. A lot of what I was working with Ying was the usability of the data. How, as an end user, what did I want to see his development of MLA deliver? You know, I wasn't about, the X-rays and how it's going to happen here and all this sort of stuff. It was about, I need information from this, and I need it generated like this. So that was I suppose, my major interactions with him. And I was very shocked to hear of his passing in 2019. So from here, I left, went west. I joined Minproc. I had an erasable business card because the names kept changing. And now I'm with Wood. And Wood is a global company that has offices. Basically, the head office is Aberdeen, its heritage is out of oil and gas, but now it's a global company working across the spectrum in terms of mining and minerals, obviously, but oil and gas, nuclear, environmental, it keeps going. And there's close to 40,000 people in the Wood organisation across the globe. And I'm still with them, but I also do a bit of independent consulting these days. Yeah, mostly things that interest me, like mineral problems. So this was one of the unusual ones I came in contact with in this particular project, which didn't end well for the company. There was a few problems with getting money, those sort of things. But we were being told, hey, there's some soluble uranium minerals sitting in this ore, and this ore's in Tanzania, and these soluble uranium minerals are within a few meters of the surface in a rainy environment. And the client was also saying, hey, we can recover this uranium just with water. Now, there's some truth, there's bits of truth in all of that. The minerals were certainly there and just under the surface, and they survived how many millennia or whatever in that situation as soluble, water-soluble minerals within a few meters of the surface. And these are just examples from elsewhere of that particular mineral that was being described as clay with M&Ms in it. These nicely coloured bits of mineral. And this is the actual ore from one of their reports, their public reports. And this is the mineral, schrockingierite, which took me a long time to learn to say. And the unusual bit about this, because it was only in clay, okay, that was part of their description. But the clay was the hardest, most difficult clay that I have ever seen. And this is the reason why a few meters below the surface, you had water-soluble uranium sitting in this ore and available for recovery. The water would not get through this material. Effectively, the scrubbing for this was milling. It wasn't scrubbing. Scrubbing is 0.5, 0.3 kilowatt hours per tonne. This needed about 5 kilowatt hours per tonne of input just to break the clays down to get to a point of having access to these uranium minerals. So there was all sorts of aspects about this which were almost true, but not quite true enough. Another one was that there were other uranium minerals there. So if you leached it out, you had a tailing which was 1,000 ppm uranium. Now, I'm not sure if people are going to be quite very happy with disposal of tailings at that level of uranium in it anyway, when typically it's down at 10 ppm from other leaching systems. The how, and I've just described this slide, basically the impervious nature of the clays. Now, there's a mine out there called Kamoa, which some of you may have heard of. When they first found it, they were getting intersections of 3% copper. They decided to go elsewhere, and because they knew the mineralization was probably over there somewhere, and they went into it, and it came out at 6% copper. And then they went somewhere else, and they drilled a few holes, and they said, 12% copper. So over a number of years, it just kept changing and getting bigger and bigger and bigger. But the whole issue of, or the biggest issue with Kamoa was liberation of the copper, the chalcopyrite, and the other minerals. And each of these intersections, going up in grade, actually had similar amounts of copper mineral. So the 12% had pure chalcocite, and the 3% had pure chalcopyrite within the system. Similar mass percentages of copper mineral, but wildly different grades. and it is now started up and is operating very nicely. But as you can see here, there's a number of different sizes here: 212 micron, 106 micron, 53 and 38 micron from left to right. But even at 38 micron, liberations of the mineral 70%, plus a little bit of highly liberated material and some high grade middlings, taking it to somewhere near 80%. So you still got 20% of the material at 38 microns that is not liberated. And when we had a close look at this, and this was in the early days, I was involved in the work on the first core that came out of this deposit for Ivanhoe. And the big thing you could see was what they were calling comets, which was clasts within this ore, which had chalcopyrite copper mineralization on one side of the clast. And we're talking, a 5 millimeter clast there, or 3 millimeter clast, or something like that. So this is big copper sitting next to it. However, when we go into that little inset, there's spots of very, very fine chalcopyrite all the way through the matrix. And we then used that and said, okay, let's apply this to the thinking of how this is going to be treated. And very quickly, it came up with a flow sheet that involved both coarse and fine liberation. And I think in the final version of this circuit, the fine side of things was down to 10 micron grind. But at coarse grinds, you could make very nice concentrates with 70% of the copper. And then you had to work on the other part of the ore and get the fine chalcopyrite out by grinding to 10 microns. And as you can see, the overall recovery's pretty good, nearly 90%, and the grades are very nice as well. When we first worked on this, there's a nice bright green section in the middle of the Kamoa area. And this is, I think each of those squares is probably at least a kilometre. I didn't check. But, oh yeah, there we go on the bottom. No, it's each of the squares is 5 kilometres. So this is the sort of scale we're talking about. So when I was there, that green area, Kamoa number 1, was what we were working on. That's what we knew about. And then in the Kakula area is where I think the 12% stuff was intersected. And that's where funnily enough, that's where the first mines started up, in that area. And interestingly, this mineralization is a bit like a coal seam, and it goes in all directions, and it's about 20 meters thick, and it follows the geology of sandstone that underlies everything here, and comes to the surface in places, but is 1,000 meters down in others. So the flow sheet that's been implemented retains this coarse and fine grinding that we developed within months at the start of this project. And had we not been looking at the mineralogy, we would not really have known the direction to go in, but the mineralogy was a clear pointer as to where we should go. So that was interesting. Unfortunately, another engineering company got in there and built it, but that was that's another story. Another one I was dealing with pre-COVID was in a phosphate concentrator in Saudi, and it had one of the simplest mineralogies you can ever imagine: quartz, calcite, and phosphate mineral, whatever that was. And the quartz and calcite were basically just that, quartz and calcite. And their compositions were stoichiometric. They were as it was written on the box. But I was a bit worried about what was in this darker phase, because it wasn't really behaving like apatite. It wasn't behaving like something else. It wasn't really fitting into a mineralogical box. So I then started to get ALS in Perth to delve in to find out what was going on with this phosphate mineral. And So under this is a typical QEM scan image, which has identified the phosphate mineral as it's all anything with phosphates just thrown into a box. Interestingly, you can see nodules there, which are all about 500 to 300 micron in diameter, and that's the phosphate mineral itself. And you can see this cement holding it all together of calcite, which was pretty amorphous, but pure calcite. And that in itself was unusual. Then we started having a very close look, and we did some high definition QEM scan. And instead of calling everything phosphate, we had a range of things we called apatite, but with various compositions. And you can see that the phosphates were not a single mineral. And there were some really good examples of very strange things sitting in there. And when you look at them and realize that this is mostly fish bones, you then understand why this is not your typical mineral system. And the apatite composition was from 9 to 16% phosphorus. As I said, they're fish bones, and in fact, you can see a backbone, the X there, and you can see a long bone running down the left-hand image. So yes, there was all sorts of interesting features in here, which is not what you expect to see when you're dealing with minerals, but that's what happens when it's generated in this fashion. Will that mineral behave consistently in flotation, or as they were doing? Will some of it float when it shouldn't, because we were trying to float calcite, trying to float silica and leave the phosphate. They were having terrible recovery problems, terrible operational issues. So that was, I think, very one of the more educational mineral exercises I've had to deal with, just in terms of what can be there when nature, biological processes are involved in producing the minerals we're targeting. And a more recent thing I've been doing is looking at some lithium operations, and in one of them, and I won't identify this one or where it is, we have got difficult liberation issues. We have unusual minerals. The lithium is contained in a thing called petalite, which is like spodumene, but it's not. And it doesn't float in the same way as spodumene floats. It has other properties. And even though the chemistry looks almost identical, it behaves quite differently. And the test work wasn't working very well. So we then started to have a look at things. And in the lithium industry, dense medium separation is the go-to first approach. And for that, you need coarse liberation. However, in the +1 millimeter size, the liberation, the blue at the top, the very little of this particular mineral is liberated and available for recovery by dense medium. So we're almost forced into a situation where the whole lot has to be ground. You can't take out a nice concentrate at the front and then have a maybe a small flotation plant on the rest of it to recover some more. It's a flotation plant that's got to deal with the whole ore. It does get better as you grind finer, the liberation, but it's also you still need to get to fairly fine sizes under 100 micron before you get decent liberation for flotation. Now, this is very unusual for a pegmatite, and this particular pegmatite has been metamorphosed. So it's pegmatite means large coarse grains. This was once, but geology and time has changed that. We also, in this situation, did LA or laser ablation, ICP-MS analysis to work out exactly what the compositions were of the various elements. And we found out that the petalite itself has a content of lithium, which is almost 10% above what it says on the box. So again, If you just assume things, you never quite know what you've got. There was another identification in this project where we had corundum being identified by QuemScan. However, QuemScan does not see lithium or beryllium. So both of these things, the corundum basically is pure aluminium oxide, and that's what it showed up as because beryllium's not detectable. When we did the laser ablation, and laser ablation, for those who don't know, is a bit like a 30 micron drill of a laser, and then you measure the stuff that's come off with mass spectroscopy. And that showed it was 7.5% Be, beryllium. And it was actually the mineral very rare called chrysoberyl, which now, when you know that, it's a very hard mineral and it's readily floatable. And then we looked in places where it might have turned up, and there it was. We were already recovering this stuff, and beryllium is an extremely rare metal. 300 tons a year are made in the world. So if you don't understand your mineralogy, there can be things hidden from your view. And I've seen that often. So I'm bringing it to the conclusion. My first approach is don't believe what you're told. Just question anything that is given to you, and especially if the results are not consistent with what people are telling you. You know, people might tell you this is a lead zinc. You float your lead, you'll get this con. You float your zinc, you get that con. There's a bit of copper there, and it's all good. You do the test work and it works. Other times you do that and you can't get the zinc out of the lead, and you can't get the lead out of the zinc, and the copper goes everywhere and all this sort of stuff. And then you say, well, why? And that's when, as soon as you ask that question, you've got to get into the minerals and understand it. As I found with Kamoa, liberation can be easy and difficult within the one sample, within the one ore. And you can get stuff easily if you know the mineralogy, and you can get stuff after you grind to 10 microns. But if you looked at it and you were just trying to chase your high recovery and high grade, you might decide that you've got to go all the way to 10 micron to get it all. And your energy consumption is huge. You can't do it. So sometimes just knowing that very quickly can set you on the right path very early in the scoping levels of this sort of work. Clients usually want the impossible, and sometimes you need to prove that what they want is actually impossible. And get the evidence, lay it out in front of them. Often you'll see, and I've heard it from many people, this ore body has been studied to death. Decades of exploration, drilling, nobody's actually been able to make it work, To me, that says there's stuff here that people don't understand. Let's get to the fundamentals. What are the minerals that are in there? Why are they behaving the way they're behaving? What's the liberation like? What's their composition actually, rather than what you think it is? And we can look much deeper these days than we ever can, and we can look much smarter these days into what is actually happening in these mineral systems. And don't be afraid to get out there and use these tools that we have available. They're often expensive, but they're often a one-off or a very limited application to actually get an answer. So don't just do mineralogy. Come up with a mineralogical question and then solve that problem with the tools available. And that's the end of my little presentation. Thank you for listening.
All right. Thank you very much, Tim. It was a very good presentation, very interesting. Shows a lot the complexities of the minerals, how important it is to geologists and metallurgists work together, right? To get a better outcomes. So any questions on the audience?
Thanks for the presentation, Dean. My name's Ray Koenig, and I worked down at Savage River a few years before you were down there, between 74 and 81.
You
and
probably knew the answer to the problem.
No, I didn't. We didn't have that problem. all bodies are not homogeneous; they're heterogeneous, and titanium was the least of our worries in the upper part of the deposit. But I guess as it got further down, titanium became a problem. And I've looked at the grades concentrate grades coming out of Savage River recently, and they're quite low in iron. I used to get, if I got less than 69% iron in a concentrate, I was.
What are they doing now?
Oh, it's only around 65%, according to the text reports.
Are they trying to be as good as some of our Western Australian iron ore deposits who struggle at 65?
Yeah, and I don't know whether that's all caused by the titanium or what. But and I guess that's one of the issues you must have seen when you're trying to figure out the plant design for a deposit, and it changes over time. You have to look at what it's going to be like in 5 years, 10 years, and 15 years. And
that's geometallurgy. Yes.
Yes, that's exactly
that's getting
right.
the right samples and hopefully believing what the mining engineers tell you is going to happen over the next 5 years or 10 years.
Yeah, that's right. And it's the importance. And I guess you found that working and designing plants at Wood and AMIC, yeah.
Yes, yeah. Typically, we try to sample. I try to make sure we have a variability sample, or lots of variability samples. By lots, I probably mean 20 or so. Sometimes in big projects, you'll get up to 50, 60 or 100. But most projects, especially at the early stages, you're probably content with getting 20 and then comparing the behaviour of those 20 different samples and have them spatially representative, because the geologists will tell you this is that rock type and this is that rock type. So what I try to do then is say, well, give me 3 examples of that rock type. Are they actually the same? Do they mean anything to me as a metallurgist? So I'm trying to arrive at geometallurgical lithologies rather than geological lithologies and say, oh, yeah, those 3 are quite different, even though the geologists call them the same. But these 6 over here all behave the same. And geometallurgically, they're the ones, that's one group. And there's another group sitting over here of material that behaves in a similar manner metallurgically in separations.
Yeah.
And at Savage, that was one of the things. In fact, we went down there and they was trying to tell us that it was going to have hard ore, because one of the things is how fast it grinds, especially with fully autogenous milling. And we went up into the pit and we're walking around with a geo hammer, and they said, oh, here's the hard stuff. And you hit it and it falls apart. And then, maybe it's over here. And the geos then took us somewhere else and we hit another hammer. And then about 6 places into our search for the hard rock, we started hitting something and sparks were flying. Okay. And they said, oh, we're not going to see that for 6 years. And we had just set the plant up to restart for Australian Bulk Minerals for hard rock. And it wasn't performing anywhere like it should have been for hard rock. And that was because it was never seeing hard rock. So, yes, geomet is absolutely essential.
That was a problem. Fortunately, they had totally stores that in a ball mill.
Yes.
And times the power was limited in the top of the store.
Yes.
Other times it was the ball mills.
Yes. Well, that's what blending eliminated.
Yeah, it would do.
Because the behaviour was sort of, here's the maximum. There was a maximum over a range of properties, and then it fell off for ball mill limiting and ag mill limiting. And the blending kept it in that maximum range and gave them tonnes.
Right. So we have an online question from Emmanuel. So he asks, drawing from your personal experience, what tests must be performed in order to know your minerals? So let's say, like, for example, if you're going for a geomet study, which tests are you going to be routinely do, like MLA or assays?
If I don't understand very much about the ore, then I will typically try to get a composite sample and get its mineralogy defined and do it by particle size as a first step. That will tell you how how all the minerals liberate in something like QuemScan MLA, and give you the overall picture of liberation by size. That can then direct you into whether there's possibilities of dense medium separation at coarse sizes, or whether you have to go for flotation, or whether there's minerals you'll never get because they're so finely unliberated that you'll never separate them. So, and that also allows for the identification of unknown minerals. And for this lithium project, that's exactly what I did, liberation by size. But I then said, send samples off to Codes, I think in Tasmania, and have the microprobe or the laser ablation performed on all the major minerals. And this is where we found the beryllium mineral, which nobody suspected was even there. So, and we found that the lithium minerals were higher in Li than the chemistry would suggest they should be. So, all of a sudden, that information can be put back into your QuemScan mineral definition, because all QuemScan does is it looks at some point for milliseconds, gathers enough information, sees a couple of peaks, says, right, that's going to go into the bucket of magnetite or chalcopyrite, because it's got peaks for copper, iron, and sulfur, and they're about this ratio, and bang. It doesn't measure precisely what that is. It comes up with a bucket that it can be thrown into. If you want to know what the minerals are, you've got to get in there and delve much more deeply with something like laser ablation. And that's what I do. Once I understand liberation characteristics and what the minerals are, then you've got a path forward. And later, I would use mineralogy for understanding separation problems that arise. So I would use it for answering specific questions that you think it's going to work here, but all of a sudden half the stuff you thought you were going to recover is not recovered. So you then do some targeted mineralogy.
Then we have another online question. What is the next frontier in the mineralogy space? How do we overcome stereological errors with the current system, so MLA, QuemScan, etc.?
Yeah, I think from my perspective, the stereological problems do not generally impact the interpretation. If you have to get to the point of worrying about those problems, you're probably going beyond the accuracy of the method to some extent. It can be important, especially where there is material that you think is showing up as highly liberated, but in fact, there are bits of something else sticking to every grain somewhere, but it's out of the plane that you've been looking at, because you have to polish a section and cut through minerals. If you can imagine a particular mineral, if a blob of something else is next to it and you slice across there, you'll see it. If that blob is under here or up here, you won't know it's actually there. And if there's a lot of those, it may be causing contamination in a concentrate, but you can never define that those blobs are in fact as prevalent as they don't appear to be without stereological correction. So for me, I don't typically worry too much about it. I understand what it will do to the numbers, and when I see things that I'm concerned about, then I say, okay, well, allowing for stereological problems, then we'll assume that this has happened or that's happened. I think, and there's been a lot of work even when I was here in tomography, 3D mineralogy, has going on for quite some time, but I'm not sure how that is going to feed in I think it's got probably more of an application in the liberation side of things, where you can understand in 3 dimensions what the liberation issues are likely to be, how difficult it is to get to that valuable material. I'm not going to say that we have all the tools we need, because tomorrow somebody here will come up with a better way of looking at it. So from my perspective, I've moved from people looking down microscopes and counting grains and deciding whether it's a binary or a ternary at Broken Hill to counting 5,000 grains in a particle size fraction in a QuemScan MLA and getting information you could never dream of. So across my lifetime, I'm happy where we are, but that's not to say that the next 30 years, 40 years won't bring something even better. I don't know what it is. I'd be rich. Can we put the air conditioner back on, please? Kim.
Hi, Dean. I agree that going to 3D for diagnosis is probably not necessary because we understand the system. But one of the reasons why we're probably revisiting it a little bit is because of the need to do simulation with liberation. When you're not got the right numbers, I think we're missing the relationships that are there. The other thing that I was wondering about is it'd be really good to be able to do online mineralogy. Do you think there's ever any technologies out there that have the scope for that, or are we a long way away from it?
I think it's good that some operations now have their own MLA QuemScan unit or whatever, and can very quickly grab samples, prepare them, analyze them, and come up with some answers about what's happening. It's a bit different to Broken Hill, where you would go out with a pan, check the tailings to see if there was any sphalerite or galena being lost to tailings at the time. But yeah, in terms of the 3D stuff, I think from the point of view of the work that you've been involved with, I think it has significant potential application. From the point of view of the stuff that I'm doing, it's hard enough to get the clients to spend the money on QuemScan. I argued with the Saudis for 2 years to get one QuemScan or a set of QuemScan results. It's very hard to get the information, and that information probably is like the Pareto, 80% of what you want, 90% of what you want can be got with that technique. It's far better than just guessing.
Right.
Was there another part to that I missed?
Oh, no, I was just wondering whether there was
online stuff. Yeah, representation, dealing at the mineral level in a float circuit. Can you do it? Yeah. Put it this way. We'll give that one to Elon and see if he can come up with something. But yeah, 50 years from now, 30 years from now, maybe it'll happen. There'll be a robotic preparation of samples, analysis, and instead of getting an assay online, you'll get the mineralogy.
Right. So I think we still have like a question line, but I think we're on time. So let's please thank Dean again for the nice presentation. Thank you, Dean. And next week we have John Bishop from Direct Lithium talking about, it's a very interesting topic as well, lithium extraction from geothermal and oil field brines. So hope to see you all next week. Thank you.